This is General Physics 1, PH 1156, and we're in Chapter 11 doing problems. The first problem we're going to do is number 1. A particle undergoes simple harmonic motion with a period of 0.21 meters in amplitude. So my amplitude's that. What is the total distance traveled in one period? Okay, so that means it starts at some place, it goes up, it goes down, it comes back. So one answer could be 0, it doesn't go anywhere, but the right answer would be it goes up and it goes back. So it would be 0.21 meters times 2, and 0.42 meters would be my final answer. Number 2, a spring of a car. I have mass of the car 1700 kilograms. Compresses 0.005 meters, not very much. When a driver, 66 kilogram driver, gets into the car, if the car goes over a bump, what will the frequency of the oscillations be, ignoring the damping? Okay, so what we have to do is we have to come up with the K of the spring. So what is that? Well, maybe we don't have to come up with the K of the spring. What is the frequency of oscillation? Well, we'll start with force is equal to kx. Okay, so I've got some force, and the force is going to be 66 kilograms times 9.8 meters per second squared, and that's going to be equal to k times x 0.005 meters. So my K is going to be 66, 9.8 divided by 0.005, and I end up with units being in kilograms, meters squared, kilograms, meters squared per second squared. All right, 66 times 9.8 divided by 0.005. 1.3 times 10 to the 5th. 1.3 times 10 to the 5th. All right, so now the issue is, what is the frequency? Well, we know that the period of the oscillation is going to be two pi m square root of m over k. 2 pi square root of m over k. And so we have 2 pi square root of, and the mass is going to be the mass of the car plus the person, 1766 kilograms, divided by 1.3 times 10 to the 5th. Alright, alright, that's good. Square root of 1766 divided by the answer that I just had, square root of that times 2 times pi, and I end up with 0.734 seconds. And I want to know the frequency, and the frequency is 1 over the period. So 1 divided by my answer, and I end up with 1.4 hertz. Okay. Number 5. A Fisherman scale stretches 3.6 centimeters when a 2.4 kilogram fish hangs on it. Alright, so we got a scale, and I got some rest position, and when I put on the fish, looks sort of like a fish. I'm going to stretch 0.036 meters, and I've got a 2.4 kilogram fish. What is the stiffness of the spring? So K is equal to the force divided by the distance, and my force is 2.4 K times kilograms times 9.8 meters per second squared divided by my distance, 0.036 meters. Didn't I just do that? Yeah, force divided by, yep, that's what it is. Alright, so 2.4 times 9.8 divided by 0.3036. 653, we'll call it 650. 650, and then we'll check to see what I think my units of K are. Newtons per meter, that's what I thought they were. Newtons per meter. Alright, so that's okay. So now we know A, so that's my A answer. I'm looking for the B answer. What will be the amplitude and frequency of oscillation if the fish is pulled down 2.1 meters more and released? Alright, so I'm going to pull the fish down more, an additional 0.021 meters. So the amplitude of the oscillation is going to be 0.021 meters, the amount that I pull it down. Now the frequency of the oscillation, so my period is going to be 2 pi square root of m over k, and so that's going to be 2 pi. My mass is still 2.4 kilograms divided by my k, 650 newtons per meter, square root of, and then my frequency is going to be 1 over the period. Alright, so I got square root of 2.4 divided by 650 times 2 times pi, 1 divided by the answer, and it's going to be 2.6 hertz. And that's the second part of my B answer. Okay, looking at problem number 8. A vertical spring with a K of 305 Newton per meters oscillates with an amplitude. I got an amplitude of 28.0 centimeters, also known as 0.28 meters, because we probably wanted in meters. When a mass, so I got a mass of 0.235 kilograms are applied. Okay, the mass passes through equilibrium at a positive velocity at time 0. What is the equation describing this motion as a function of time? Well, because it passes through 0 at time 0, that means I've got a sine function, so it's going to be sine of something, and then we have to calculate that something. So the period is 2 pi square root of 0.235 over 305. Square root of 0.235 divided by 305, close parentheses, times 2 times pi. That's highly unlikely. We'll have to do that again. A square root of 0.235 divided by 305, close parentheses, times 2 times pi. 1.6, we'll call it 1.63 seconds is the period. Now in a sine wave, we know the period is 2 pi over b, where this would be bx. So that being the case, b is going to be 2 pi divided by the period, 2 times pi divided by the period gives me 3.86. So we would change our equation to the amplitude sine 3.86x, and that would be the equation of that guy. Now that's the A part. At what times will the spring be longest and shortest? Longest and shortest. Alright, so it's going to be longest and shortest when the period, when time is equal to the period divided by 4, because the period would be 2 pi divided by 4 would be 90 degrees. So at 90 degrees and at 360 degrees, so at 90 degrees and at 3 pi, 3 the period over 4, which would be the 200. So this is the 90 degree spot, this is the 270 degree spot. But all it's going to differ by is a minus sign. Alright, so we're going to go and take the period divided by 4 and put it into x. Now, do we really want to do that? Oh, wait a minute. We don't have to do that at all, because we know what the amplitude is. So forget about that. Alright, so we don't know at what times. Well, we still have to figure that out. At what times will the spring... Oh, we want to find the time. Okay. So we do have to do something like that. We want to make 3.86x be equal to pi over 2, and 3.86x to be equal 3 pi over 2. So, and we'll change the x to a t. Yeah, we'll change the x to a t. That makes more sense. Okay, so it's going to be longest. No, it's going to be shortest. Shortest when t is equal to pi divided by 2 divided by 3.86. So it's going to be shortest at 407 milliseconds. And it's going to be longest when t is equal to 3 times that number, times 3. So it'd be 1.22 seconds. Okay, so that's when it's going to be shortest and when it's going to be longest. That's all there is for 8. Now we're going on to number 20. An object with mass 2.7 kilograms is executing simple harmonic motion attached to a spring with a stiffness spring constant 310 newtons per meter. When the object is 0.2 meters from the equilibrium position, it is moving at 0.55 meters per second. Okay, so here's the equilibrium position. It's going up, it's going down, it's going up. Okay. If the speed is 0.55, that means it's got to be going up. Well, the derivative of that function is a cosine function. So 0.55 occurs twice, there and there. Alright, so that's in the first quadrant and the fourth quadrant. So now the issue is I calculate the amplitude of the motion. The amplitude of the motion. The amplitude of the motion. Okay. Amplitude of the motion. Okay, well, no, that isn't doing us any good. Calculate the amplitude of the motion. Well, we know the period is 2 pi square root of m over k. So we'll calculate that first. Square root of 7.2 divided by 310 times 2 times pi. 0.586 seconds. Alright, so that's the period.
Alright, that's how you do it.
And velocity is, what is the equation? Let's see, which one are we doing? 20. Calculate the amplitude of the motion when the object is at 0.2 meters from equilibrium. Velocity. Okay, so I know the period. It doesn't make any sense, does it? Back to 20. Calculate the amplitude when the object is 0.2 meters from, okay, x is 0.2. Now I think we have enough data. If I look at I'm looking at equation 11-4c, 11-4c, and I see that 1/2 mass velocity squared plus 1/2 x kx squared is equal to 1/2 k amplitude squared. And I have enough things for all those. So I can get rid of the 1/2 by dividing both sides by 2, by multiplying both sides by 2. So that goes away. So I get 2.7 times 0.55 squared plus 310 times 0.2 squared is equal to 310 times a squared. So a is going to be square root of 2.7 times 0.55 squared plus 310 times 0.2 squared divided by 310. And that was too easy to mess around that much with. 2.7 times 0.55 squared plus 310 times 0.2 squared. Oh, I don't have enough parentheses. Okay, insert parentheses. Right. Divided by 310 parentheses. Parentheses divided by 310. Close parentheses. There we go. So I've got 0.21 meters. 0.21 meters. Oh, that's pretty interesting. So I'm almost at the top when I'm going that fast. All right, well, back to the problem. Number 20 has a B part. Calculate the maximum speed. All right, so velocity max is equal to, and I'm looking at equation 11-5a is amplitude square root of k over m. So I got 0.21 square root of 310 divided by whatever the mass is, 22.7 kilograms, newtons per meter up there. Alright, so I got second function, my answer, times the square root, 210 divided by 2.7, and I end up with 2.2. That's impossible. How can I have 2.2? How can velocity, oh yeah, velocity max can be 2.2 because the original velocity was 0.55, right? Yeah. Alright, so we'll do that. 2.2 meters per second is our maximum velocity. Okay, number 40. A cord of mass 0.6 kilograms. Got a mass 0.6 kilograms is stretched between two supports, support 1, support 2, my cord, 8 meters apart. The tension in the cord is 120 newtons. How long will it take a pulse to travel from one support to the other? Okay, so this is number 50, this is 40. 40, okay. And, from one support to the other. Okay, so my frequency, no, I don't want that. Okay. Okay, so first of all I need to have mu. And mu is going to be the mass divided by my length. So I'm going to have 0.6 kilograms divided by 8 meters. And then the velocity is going to be the square root of the tension divided by my mu. So velocity of the pulse, square root of 120 newtons divided by 0.6 divided by 8, 0.75 kilograms per meter. Okay, so square root of 120 divided by 0.075, and I left out a 0 there. But I have it in my calculator. So I'm going to be 40 meters per second is my speed. I have 8 meters to travel, so my time, 8 divided by 40, is going to be 1/5 of a second. Is how long it's going to take to travel. 50, that was 40, but it has to transpose from one support to the other, right? 1/5 of a second. All right. Number 50. I have a violin string. Its frequency is 294 hertz when unfingered. At what frequency will it vibrate if it is fingered 1/3 of the way down from the end? Okay, so I got this violin string, and I'm going to finger it right there at 1/3. So I got 1/3 on this side, and I have 2/3 on that side. Okay, so it's got to go faster, and it's going to go faster by 3/2. Okay, so 294 times 3 divided by 2, so it's going to go at 441 hertz. If I finger it there. And that's all there is to 50. Yes, that's all there is to 50. All right, 53. 53, the guitar string is 0.29 meters and has a mass of 0.0034 kilograms. The distance from the bridge to the support post is 0.62 meters. And the string is under a tension of 520 newtons. What are the frequencies of the fundamental and the first two overtones? Fundamental and first two overtones. All right. And we want the frequency. Okay. Interesting. Very interesting. Alright, so it looks like lambda of the fundamental is going to be 2 times the length. So that's going to be 1.82 meters. That doesn't make any sense. if that's the case, then our frequency would be extremely low, but I don't like that frequency.
Well, it should just kind of kick around, stay centered on that.
Force of tension. Okay. Okay, so that's fine. But the frequency is going to be the velocity of sound divided by lambda 1. Alright, so what do we know about the velocity of sound?
Let's do that for now. Let's just go with that. And then let me, any closer? All right, let's go ahead and try to do that. So go back up.
Okay, when I look at thing on page 316, we have a piano string. Velocity is lambda f. So we use the f of t, and we solve for velocity. Okay, so that's going to be our strategy. We'll go back. So we're moving back to there. We're going to say f of t is equal to mass over L velocity squared. So the velocity is going to be the square root of the tension times the length divided by the mass. Okay, square root of 520 times 0.92 divided by 0.0034. Okay, so we have 375.1 meters per second. Okay, now that I know the velocity,
I think you're doing the wrong problem.
53?
Yeah, I think you're doing 54.
Oh,
I
yeah.
just went to reread it and I'm like,
All right, back
I'm
to
reading
the right.
54.
Going back to the right problem. 53, two consecutive tones vibrate at 280 hertz and 350 hertz. What is the frequency of the fundamental? Okay, well, the difference between these guys is 60 hertz, right? 70 hertz? 70 hertz. And the fundamental times some number is equal to each of those. So the fundamental has to be 70 hertz. So the difference between those two frequencies is 70 hertz. Therefore, the fundamental has to be different than 70 hertz because the fundamental is what all the overtones are based on. Well, it wasn't that simple.
Much easier than 54.
64. 64. The length of a pendulum, L, 0.72 meters. The pendulum has a bob of mass 0.295 kilograms. It's released at an angle of 12 degrees to the vertical. Assume simple harmonic motion with what frequency will it oscillate? Okay, so we're going to draw a picture. I'm going to release it there. There's my 12 degrees. Okay, so that's what I'm doing. So at what frequency will it oscillate is the first question. And this is simple harmonic motion. And frequency is equal to 1 over 2 pi square root of G over L. 1 over 2 pi square root of 9.8 meters per second squared, 7.27 meters. All right. Square root of 9.8 divided by 0.72 close parentheses divided by 2 divided by pi. 587 milliseconds. Hertz is what we want, so we don't want milliseconds. So we want 0.587 hertz. This is 64. What is the frequency? What is the pendulum's speed when it passes the lowest point? Okay, so the issue is, this is 0.72 meters. We want to know what this height is. That's the issue. We got to know that height. Okay, so if I use a cosine function and I say the cosine of 12 is equal to L over 0.72, and that gets this L right here. We could call, why don't we call it H? H over 0.72. And so we got that H is 0.72 times the cosine of 12, and my calculator is in degrees. So I have 0.704. So the distance x that's different is 0.72 minus 0.704. And so the change in the distance, so 1 minus my answer, not 1, 0.72 minus my answer. Okay, so I've got 0.0157 meters. Now, mgh has to equal 1/2 mass velocity squared. I'm all kinetic energy when I'm at the top. I'm all potential energy on the top. I'm all kinetic energy on the bottom. Those two guys have to equal each other. All right, so mass, which I forget what my mass is. So 0.295 kilograms times 9.8 meters per second squared times h, 0.0157 meters times 2 divided by m, 0.295. Take the square root of it, and we end up with velocity max. And we see that we have mass on both top and bottom, so we can get rid of them. Square root of 2 times 9.8 times 0.0157, close parentheses, and I end up with my max velocity being 0.55. And how many significant digits do I think I have? I think I have 2. Okay, meters per second. Now that's my max velocity. So that's my B answer. What is the total energy stored in this oscillation, including no losses? So energy max is going to be mgh, 0.295, 9.8 meters per second squared, 0.0157 meters. And my answer would be in joules when I got done pointing, times 9.8 times 0.05157. Boom. And so I'd have 45 millijoules. Okay, that was all of them. So now we go to 72, 73, my mistake. Go to 73. Oh yes, we have a car mass of 950 kilograms. And it strikes a spring. My velocity is 25 meters per second. Compresses the spring. X is equal to 4 meters. What is the stiffness of the spring? Stiffness of the spring. So force is Kx. Alright, so I got what's my force? Mass times acceleration. I got some kinetic energy. My kinetic energy is 1/2 mass velocity squared. Alright, so 0.5 times 25 times, no, 0.5 times 950 times 25 squared. Alright, so I got not 2.96 times 10 to the third joules. Force is work. Work is force times distance. So that number of joules I have 2.96 times 10 to the 5th joules divided by the distance, 4 meters, will be my force. Okay, so I'm going to divide my answer by 4, and I get 74 kilonewtons. Okay, so 74 kilonewtons, my K is going to be that force, 74 kilonewtons, divided by 4 meters. So the spring constant divided by 4, 18.5 kilonewtons per meter. Okay, so that's my spring constant. How long is the car in contact with the spring before it bounces off in the opposite direction? long is it in contact with the spring? That begs the issue. As the string expands, it's going to start slowing down. So I'm going to be at contact. I'm going to push it in. Okay, so here's my spring. The car hits the spring, it compresses the spring, the car then moves back out. When it gets back to that equilibrium position, the car is going to continue going, the spring's going to start slowing down, and I'm going to lose contact. So that means that I need to find the frequency of the spring, or the period of the spring, and it's going to be half the period is what the answer is going to be. So the period is 2 pi square root of mass over k. Now I don't know the mass of the spring, do I? Only the car. So we'll assume that the mass of the spring is small compared to the car. So 950 kilograms divided by 18.5 kilonewtons per meter. Okay, so 2 times pi times square root of 950 divided by 18.5 W3 close parentheses. So it's going to be 1.424 seconds. And we said we wanted half the period. So we divide that by 2. And we end up with 0.71 milliseconds. And then we ask ourselves, how many significant digits? It appears I only have 2. So I would go with the car is connected to the spring for 0.71 milliseconds for the B answer. That seems awful quick. Awful quick. This is 73. So we can check out and see what the author thinks. Not that we really care what the author thinks, but we can still check it out. So 11:40:73. It says a half second, but it says that we're 3.7 times 10 to the 4th Newton meters. 3.7, so we're twice as many. This is supposed to be 3.7 times 10 to the 4th. So we'll go back and, so that's twice that number. Alright, so how did I get that? I wonder, I got here, I got that number. Did I do that right? 0.5 times the mass, 950, times the velocity, 25 squared. Yeah, that's right. This is a 5. And so that's the kinetic energy. Kinetic energy is force divided by distance. That divided by the distance, 4, divided by 4, gives me that in kilonewtons. K. Kx. Compresses the spring 4 meters. So I divide that by 4. Why would my stiffness be twice that amount? And the answer is I don't know. I like our answer better than the book's answer, which is what we'll go with. Okay, good enough. We'll all right, I'm back on. We're revisiting the answer for 73. Okay. And what we're going to say is that the spring constant is going to be mass velocity squared divided by distance squared, which is going to be mass, which is going to be 950 kilograms, 25 meters per second squared divided by 4 meters squared. And that my spring constant is going to be 37 kilonewtons per meter. Okay, so that's my A answer. And then for my B answer, I'm going to say I want 1/2 the period, which is the same thing I said last time that I wanted, 1/2 the period, which is going to be 1/2 2 pi square root of mass over K, which is going to be pi square root of 950 kilograms divided by 37 kilonewtons. 37 kilonewtons. Okay. Pi times square root 950 divided by my answer, and I end up with a 1/2 second. Okay, now it's time to quit.